Hi, good morning, everyone. My name is Sarah. I'm from the Department of Human Health and Nutritional Sciences at the University of Guelph. I've been working with Dr. Alison Duncan on a project to examine the effect of resistant starch bagels on glycemic response in adults at risk for type 2 diabetes. And so type 2 diabetes is a growing concern in Canada and around the world. 1 in 4 Canadians has prediabetes or diabetes, despite the fact that type 2 diabetes can often be prevented with improvements to dietary and lifestyle habits. Of particular interest, increased fiber consumption is often associated with a reduced risk of developing type 2 diabetes, but the majority of Canadians do not consume enough fiber each day. And this really highlights the opportunity for high-fiber functional foods to be developed in order to help reduce this risk by providing more fiber and filling the fiber gap. And resistant starch is a high-fiber ingredient that can be incorporated into functional foods. But what is resistant starch? Resistant starch is considered a starch botanically, but when it's consumed, it behaves like a fiber in the body. And this is because it's resistant to our digestive enzymes. It's not broken down into glucose in the small intestine like regular starch. Instead, it passes largely undigested through the GI tract until it reaches the large intestine, where it's fermented by the local bacteria. There are 4 subtypes of resistant starch, and they're each classified based on the reasons that make them resistant to our digestion. But I'll be focusing on resistant starch type 2, as it's most commonly studied for its health benefits. And RS2 is resistant to our enzymes due to the tightly packed conformation of the starch within the starch granule that limits the digestive enzyme access. And RS2 occurs naturally in low levels in corn, some legumes, and unripe bananas, but varieties of corn have been selectively bred to yield higher amounts of resistant starch. And this corn can then be processed into a flour and incorporated into baked products. And so, as a result of this, a number of human interventions have been conducted in order to examine the effects of resistant starch consumption on glycemic control. Looking at the literature, they can all be divided into acute interventions and chronic intervention studies. And within these categories, they can be divided into those that look at resistant starch supplements and resistant starch foods. So starting with the acute resistant starch studies, what these studies measure is the postprandial glucose and insulin response to a food or supplement that contains the resistant starch. There is some variation in the study designs used, but overall, these studies show that acute consumption of resistant starch can reduce the postprandial glucose and insulin response. And so the next logical step is to determine if longer-term consumption, chronic interventions, can improve the overall glycemic response. And chronic RS studies do this by measuring insulin sensitivity and resistance, as well as the fasting and postprandial glucose and insulin response. There have been a number of these studies conducted, but they suffer from a great deal of variation in the study designs used with respect to participant characteristics, the dose, the form of resistant starch use, also the duration of the intervention, and especially they vary in the methods by which they assess the glycemic response. And all of this variation leads to mixed results overall. And so we know that type 2 diabetes is on the rise despite the fact that it may be prevented with improvements to dietary habits such as increased fiber intake. We also know that resistant starch is a dietary fiber that can improve the acute postprandial glycemic response. However, further research is needed to determine if chronic consumption can improve the overall glycemic response. And so this is why we conducted the Better Bagel study. The purpose of the study was to determine if 8 weeks of consumption of bagels that can provide about 25 grams of resistant starch per day can significantly improve markers of type 2 diabetes compared to a bagel without added resistant starch in adults at risk for type 2 diabetes. And it was hypothesized that this treatment would significantly reduce fasting and postprandial glucose and insulin. And so to test this hypothesis, we conducted a randomized crossover trial out of the Human Nutraceutical Research Unit at the University of Guelph. Participants completed a 3-step screening process and an orientation visit. They were then randomized to consume one of the 2 treatment bagels for the first 8-week treatment period. They then consumed neither study bagel for the 4-week washout period, and then consumed the alternate study bagel for the final 8-week treatment period. 25 participants were enrolled in the study who were generally healthy but had an increased risk of type 2 diabetes. And the core method of assessment of diabetes risk that we used was the Canadian Diabetes Risk Assessment, or the CAN-RISK questionnaire, which assigns an overall risk score to an individual based on a wide range of risk factors, and it's a validated questionnaire from the Public Health Agency of Canada. And so participants were asked to consume 1 bagel a day, either the control bagel, which was a standard white bread, wheat-based plain bagel, or the resistant starch bagel, which followed a similar recipe, also plain in flavor, but had 60% of the regular flour substituted for resistant starch ingredient, which was called high maize 260. And as a result of this substitution, the bagels provided 25 grams of resistant starch per day. And so in addition to eating a bagel a day, the participants attended biweekly study visits at the HNRU on study days 1, 15, 29, 43, and 57 of each of the treatment periods. Fasted body weight was measured at each study visit, and the bagels were provided to the participants in a frozen 2-week supply of bagels at each of the first 4 study visits. In addition to this, the participants completed an oral glucose tolerance test, an OGTT, at the beginning and end of each treatment, so on study days 1 and 57, in order to determine the effects of the bagel consumption on the glycemic study endpoints. So on the OGTT study days, participants arrived at the HNRU after having fasted overnight, and they had an IV line inserted into their arm. Once the participant was comfortable, the fasting or the 0-minute blood samples were taken. They then drank a standardized 75-gram glucose tolerance beverage within about 5 minutes. And once the beverage was consumed, further blood samples were taken at 15, 30, 60, 90, 120, and 180 minutes after the beverage. And then these blood samples were processed and later analyzed for glucose and insulin concentrations. From the fasting glucose and insulin data, we used the homeostasis model assessment, the HOMA model, to estimate indices of insulin resistance and insulin sensitivity, which are opposite in concept and also mathematically the inverse of one another. And also, the homeostasis model assessment yielded a measure of beta cell function as well. And then with the postprandial glucose and insulin data, we graphed the concentrations over the 3-hour OGTT period and calculated the incremental area under the curve for the first 2 hours and the entire 3-hour period. And the statistical analyses for the study were performed using SAS software with a p-value equal to or less than 0.05 being considered statistically significant. And then the glycemic data on study day 57 were compared between treatments using analysis of covariance, using study day 1 values as the covariate, and this was followed by Tukey's test for multiple comparisons. And so moving on to some of the study results, starting first with the participant characteristics. So you can see our participant sample was 2/3 male, 1/3 female. The mean age was 55, and the mean BMI was just over 30, which is considered obese. And increased age and BMI are both risk factors for developing type 2 diabetes. And in addition, the mean CAN-RISC questionnaire score was actually just over 31, which indicates a high risk of developing type 2 diabetes. And it's also important to note that there were no significant changes to body weight over the course of the study for either of the treatment periods, which reduces any confounding effects the change in body weight may have had on the study results. So moving on to some of the glycemic response biomarkers, starting first with the fasting glucose and insulin data. So here I have the data for study day 57. I'm not presenting study day 1 data for this endpoint or for any of the other endpoints, as there were no significant differences between treatments for any of the glycemic endpoints, which provides evidence that the washout period was sufficient. And so starting first with the fasting glucose data on study day 57, you can see that there was no significant difference between treatments. Looking at the fasting insulin data for study day 57, you can see that there was a significant reduction in fasting insulin following the resistant starch bagel treatment compared to the control bagel treatment period. And what this indicates is that significantly less insulin is required in the fasting state to maintain glucose homeostasis, and this is illustrating the concept of improved insulin sensitivity. We did also measure an index of insulin sensitivity using the homeostasis model assessment, and I have the results of those 3 variables here. So following the resistant starch bagel treatment period, on study day 57, there is a significant reduction in insulin resistance, which means also a significant improvement, an increase in insulin sensitivity. And furthermore, there was a significant reduction in beta cell function following the resistant starch bagel compared to the control bagel. And so looking at the postprandial glycemic response, starting first with the postprandial glucose response. On the left, I have the OGTT time curves, so the concentration of glucose for each of the treatment periods, and on the right, I have the 2-hour and the 3-hour incremental area under these curves. And so looking at the glucose response, you can see that there were no significant differences between treatments on study day 57. But looking at the postprandial insulin data, I have the same setup here. You can see that following the resistant starch bagel treatment on study day 57, there was a significant reduction in postprandial insulin response compared to the control bagel treatment period. And what this means is that after consuming the bagels for 8 weeks, the resistant starch bagels for 8 weeks, significantly less insulin is required in the postprandial state to manage the same rise in glucose. And again, this is illustrating the concept of improved insulin sensitivity. And so to sum up the results, the glycemic results of the study, you can see that there was no significant differences in fasting glucose or postprandial glucose, but there were significant reductions in fasting insulin, postprandial insulin sensitivity, and, postprandial insulin response and insulin sensitivity. The lack of differences in the glycemic endpoints are mostly consistent with the literature, but the improvements to the insulin endpoints are novel for resistant starch food studies. This is the first resistant starch food intervention to significantly reduce fasting insulin resistance measured by the homeostasis model assessment, and also to significantly reduce the postprandial insulin response following an oral glucose tolerance test. And so this research extends the literature by providing evidence that resistant starch consumption in a food can improve glycemic markers of type 2 diabetes in a food matrix in adults at risk for type 2 diabetes, and furthermore, this was demonstrated using a standardized oral glucose tolerance test. Further research is needed to clarify the mechanism by which resistant starch may improve insulin sensitivity. However, this research provides evidence to support the use of resistant starch foods as a dietary strategy to help improve markers of type 2 diabetes. Thank you all.
Time for one or two questions. Any questions? Yeah, right here in the front. Just put...
That was based in the literature, what the other studies were seeing and the results that they were getting. There was also a limitation to how much resistant starch we could fit in one bagel, and that was the most we could get in one bagel, to be completely honest. 60% was the highest ratio, and with the size of the bagel that we had, that was a bit of a limiting factor, but studies range from 6 grams to 30 grams per day. Just depends on the length of the intervention as well. Thanks. Okay, there's 2 people. Hello.
Is there any side effects by consuming the bagel?
This is my favorite question. The most frequently reported side effect was flatulence, but it was not ever reported to be a major problem by anyone. But it was just the most commonly. It was in less than 30% of participants overall, but we did measure that every other week, as well.
Was there any difference between male and female in your results?
We didn't do that analysis to split them up, so I don't know. Thanks.
Thank you very much.
Thanks.
Okay, thank you all for this opportunity. So testes, why are they important? I think we all know, but just to get a brief background on it. So the main function of testes is steroidogenesis and spermatogenesis, and any impairment in these functions leads to male infertility. It's interesting that 30% of infertility cases are actually a result of male infertility. And although it has been studied before, there are many more studies related to women's infertility, but not as many in comparison to male infertility. So what are testes sensitive to, and what causes a change in these processes? So some of the changes can be environmental toxicants. Anything from food packaging to mercury in water can lead to a difference in testes function. Secondly, diet influence, a diet high in saturated fat combined with a sedentary lifestyle can lead to impaired or changed testes function. So the third being disease conditions, specific conditions such as cryptorchidism or prostate problems can lead to impaired testes function. And the last one, being one of the more rising problems, is obesity. there are many studies that link obesity with testes function, and what we were interested in is whether diet and obesity together play a role in testes function, and how do they change testes function. So with regards to obesity, obese men quite often experience different kinds of conditions, such as low testosterone, erectile dysfunction, reduced spermatogenesis, reduced hormone production, and overall poor semen quality. What's more interesting is that sperm in infertile men shows a specific decrease in docosahexaenoic acid, and it also shows an increase in lipid peroxidation, and overall an altered balance of phospholipids. So what makes the testes so unique in their function? It's the fact that they are extremely high in lipids, some of the main lipids being cholesterol, seminolipids, and very long-chain fatty acids. Seminolipids are of special importance since these lipids are not found in any other organ of the body and have been linked to development of sperm and proper sperm formation. In addition to this, testes are also highly enriched in polyunsaturated fatty acids. Now, the levels of these polyunsaturated fatty acids can depend from species to species. For example, as I previously mentioned, in humans, DHA is known to be important for testes function. However, in rodents, especially in rats, docosahexaenoic acid, or DPA, is the predominant fatty acid. So to mimic the obese condition in humans, we had to look for a model which would give us the same symptoms and then test whether dietary effects are seen in this animal model. We used FAFA Zucker rats, which have a dysfunctional leptin receptor. Because of this, they are hyperphagic, hypercholesterolemic, hyperinsulinemic, but they are not hyperglycemic. In this diagram here, we can see that the testes of these animals are different between a lean animal and an obese animal. Especially with regards to an obese animal, some of these Zucker rats have an imbalance in their testes, leaving one of the testes completely underdeveloped and the other one fully developed. Further doing lipid analysis previously in our lab showed that, now this is a chromatogram between the normal and an underdeveloped testes. We can see that the normal testes shows a normal level of arachidonic acid, and the same level is seen in an underdeveloped testes. But when we see the next step, which is docosahexaenoic acid, it remains high in a normal testes, but in an underdeveloped testes, that level falls significantly. This shows that something must be going wrong with the elongation desaturation phases between these two fatty acids. And this could be a link to what might be happening in testes function. So our research questions were, do dietary fats influence the fatty acid composition of underdeveloped testes in comparison to normal testes? And secondly, what are the changes in overall changes in genes in underdeveloped testes in comparison to normal testes? We hypothesized that underdeveloped testes will respond to dietary fats, but not to the same extent as normal testes, and that they will also show an altered gene expression in comparison to normal testes. So our study design consisted of the lean and the obese Zucker animal. The lean animal was the control animal, which was fed a safflower oil diet, which is high in N6-LA. The same diet was also given to the obese animal, and the other two diets given to the obese animal were EPA and DHA. Thus, we wanted to see the effect of N6 and N3 fatty acids and the incorporation in the testes, and also whether there's conversion from EPA to DHA. The methods used for analyzing were the first section was lipid analysis, where we did fatty acid analysis using gas chromatography. And the second stage consisted of microarray analysis, whereby we were able to see the full gene expression profiles of testes, so not only related to PUFA metabolism, but whether what are the genes that are up or down regulated in these tissues. Ingenuity pathway analysis was then used for analyzing these data sets, and a select set of testes from this data set were validated using RT-PCR. The statistics used was one-way ANOVA for lipid analysis and Fisher's exact test, which was generated by IPA for gene analysis. So what did we find? So looking at the diet effects on fatty acid composition in normal testes in the phospholipid fraction, we can see that the level of arachidonic acid is high in both lean and controlled safflower diet. And so there's not a lot of difference between a lean animal and an obese animal in terms of this particular fatty acid. Coming to the EPA diet, we can see that as we provide supplement EPA and N3 fatty acid, the level of arachidonic acid, the N6 fatty acid, is in fact reducing. However, in a DHA supplemented diet, it doesn't reduce to the same extent. In a normal testes, we can see that there's also good conversion of arachidonic acid to DPA. But what happens when we compare the lipid profile of a normal developed testes to an underdeveloped testes? So what happens is that the level of arachidonic acid remains high in an underdeveloped testes, as we can see on the right side. And there is very low conversion of arachidonic acid to DPA. There's also a lower level of DHA incorporation. However, it's not significantly different in comparison to a normal testes. So moving on to gene analysis, we extracted whole RNA from homogenized testes. This RNA was then amplified, labeled, and hybridized onto gene chip Affymetrix arrays. These arrays were then hybridized, stained, and washed, and the resulting arrays were scanned to give us a whole gene expression profile. This raw data was then normalized for background correction, dye differences, and then the data was then uploaded into Ingenuity pathway analysis. In Ingenuity pathway analysis, we compared the data on the basis of 3 categories: between lean and obese animal, then diet differences between a safflower diet and an EPA diet, and between an underdeveloped and a normal testes. So although we did not find significant differences between the lean and obese animal, and based on the diet as well, we did find significant differences in the expression profiles between normal and underdeveloped testes. So we took the normal and underdeveloped testes, and a core analysis was performed in IPA on these data sets. So this gave us a basic map of the metabolic pathways in which these genes are being upregulated and where these genes are normally acting. And then the core analysis of these 2 categories were run through a comparison analysis to give us a side-by-side idea of what are the changes that are taking place between a normal and an underdeveloped testes. So coming to the genes involved in lipid metabolic pathways, the dark blue bars here we can see are the genes that are upregulated in an underdeveloped testes, and the light blue bars are upregulated in a normal testes. From this bar graph, we can see that the genes that are upregulated in a normal testes are involved in pathways such as triacylglycerol biosynthesis and sphingomyelin metabolism. However, the same genes are not upregulated in an underdeveloped testes. This shows that there is a difference in the lipid metabolism between these 2 tissues. Coming to genes involved in diseases and disorders, we can see that the genes that are upregulated in an underdeveloped testes are associated with diseases such as reproductive system disorders, endocrine system disorders, and more interestingly, lipid metabolism disorders. However, the same genes are not upregulated in a normal testes. So this brings me to the summary and conclusion. Firstly, in terms of fatty acids respond differently to dietary lipids in a normal and an underdeveloped testes. In terms of gene expression, the microarray analysis revealed a significant difference between gene regulation and lipid metabolism of underdeveloped testes in comparison to normal testes. So what can the future direction be? So we know that lipid metabolism plays a major role in testes development, and it is in some way linked to impaired testes function. And fatty acids play a major role in the development and size. So further research can be conducted, especially with regards to N3 and N6 metabolism and whether the enzymes acting in these metabolic pathways are in some way inhibited or are not acting to the same degree. And that could be causing an underdevelopment in testes. So at this moment, I would like to thank my committee members, my supervisor, Dr. Mi-Young Seo. This project was in collaboration with Dr. Taylor's lab from the University of Manitoba and also the Department of Animal Science. I would like to thank the summer students in our lab and the University of Manitoba Research Grant Program and the NSERC Bridge Funds. And thank you all for listening.
We have time for one question over here on this side of the room. Yeah.
Was there any difference between the frequency or magnitude of cancer development in the testes when you fed DHA? So was there really any change in testes size or the frequency?
Well, what happened was that the imbalance that we saw between testes was not that we saw in the other diets was not seen to the same extent in a DHA supplemented diet. So these diets were administered for 8 weeks, and at the end of 8 weeks, we saw that the DHA supplemented diet, in fact, showed balanced testes. And even when we analyzed sperm morphology, the DHA supplemented diet showed relatively better and more number of normal sperms compared to the other diets, which actually showed, in the obese animal, which actually showed a lot of sperm abnormalities, such as abnormal head or an abnormal tail, or in general, a low number of sperms. So a DHA diet, it did indicate that a DHA diet does in fact help in proper development of testes.
Hi, everyone. Thank you for being here, and I would like to thank the selection committee for giving me the opportunity to present a portion of my graduate work titled Increasing Hepatic DHA Levels Through Dietary Supplementation with DHA, but not EPA or ALA, Prevents Hepatic Steatosis in FA-FA-Zucker rats. To start off, hepatic steatosis is clinically defined as the intraaccumulation of hepatic fat, with the least severe form being non-alcoholic fatty liver disease. But if non-alcoholic fatty liver disease is left untreated and unmanaged, it can lead to non-alcoholic steatohepatitis, which includes necrosis and fibrosis of the liver. Insulin resistance is also closely related to hepatic steatosis, as in hyperinsulinic states, there is an increase in triglycerides leaving the peripheral tissues, which enter the liver. And from there, this free fatty acid entering the liver is unable to be re-esterified to leave the liver and go back to the peripheral tissues. This further leads to an increase in hepatic triglyceride accumulation. Now, omega-3 fatty acids are polyunsaturated fatty acids with a double bond from the third carbon from the methyl end of the carbon chain. Alpha-linolenic acid, or ALA, is an essential fatty acid in our diet. ALA can be further converted into EPA or DHA, which are eicosapentaenoic and docosahexaenoic acid. So here's just a general summary of how this theoretically works. We have ALA, which is an 18-carbon omega-3 fatty acid, generally found in plants, such as flaxseed and canola oils. It can be elongated and desaturated to form eicosapentaenoic acid, a common marine oil, or EPA, which is 20 carbons in length. And finally, we have docosahexaenoic acid, which is another marine oil. And this is formed from EPA through another series of elongation, desaturation, and beta oxidation. This all leads together to form the rationale of my study. Some research evidence suggests that fish oil can have beneficial effects on hepatic steatosis and insulin resistance. But in the past, investigation in relation to an omega-3 fatty acid source from plants have yet to be done. Furthermore, past studies have shown that hepatic steatosis patients have a lower omega-6 to omega-3 PUFA ratio in their livers. And finally, although past research has used marine oils, a direct comparison of EPA to DHA consumption on hepatic steatosis and insulin resistance have yet to be done. This leads to my hypothesis and objectives. The hypothesis of the study is that a dietary intervention from plant-based sources, such as ALA, will be as effective as a dietary intervention from a marine source, either EPA or DHA, at improving insulin resistance and preventing hepatic steatosis. From there, the objective of my study was to determine the effects of an 8-week dietary intervention study with various polyunsaturated fatty acids, so PUFA, compositions, with ALA, EPA, or DHA. And these diets all contain similar portions of saturated fatty acids, monounsaturated fatty acids, and polyunsaturated fatty acids on hepatic steatosis and the associated parameters. In relation to my experimental design, there were 6 groups in the study. There was a baseline group that was terminated at week 0, which was fed a baseline diet of soybean oil. There was 3 omega-3 fatty acid fed groups, which contained 10 FAFA saccharats in each group. One group fed a plant-based source of omega-3s, one fed a source from EPA, and one fed a source from DHA. These were all compared to 2 other groups, which were fed linoleic acid, or LA, from safflower oil, and each of these 2 groups contained 10 FAFA saccharats, or 10 lean rats. Furthermore, all the diets contain 10% weight per weight of fat in their diets, with 3% of the 3% of the fat coming from an omega-3 source. At week 8, the rats were fasted, and an oral glucose tolerance test was done. Liver samples were collected at week 8 termination, and liver sections were used to assess hepatic liver lipid droplet size, and portions of the liver were also used to assess total liver lipid analysis. Furthermore, the fatty acid profiles, so the phospholipid fraction and the triglyceride fraction, were detected using gas chromatography. Now on to the exciting part, results. We can see here that total liver weight did not differ amongst the fatty groups, but you can see that the ALA-fed group did exhibit the highest degree of hepatic steatosis, as shown with the highest amount of total liver lipids measured through using the Folch method. Furthermore, the DHA group exhibited the lowest degree of hepatic steatosis amongst the experimental FAFA saccharats, and this was similar to the baseline group. In relation to hepatic liver lipid droplet size, you can see visually that the FA-ALA had larger liver droplets, while the FA-DHA had smaller liver lipid droplets compared to the FA-ALA. In relation to the average liver lipid droplet size, there was no statistical significance among the groups. But you can see in relation to the groupings, the FA-DHA did exhibit smaller liver lipid droplet sizes compared to the EPA and ALA, and the FA-ALA had larger liver lipid droplets among the larger measured intervals. And these analyses were measured using the chi-squared analysis, which confirmed that there were differences among the groups in relation to hepatic liver lipid droplet size. In relation to the triglyceride omega-3 fatty acid accumulation, you can see that the diet generally reflected what was found in the triglyceride fraction, with the ALA having the highest amount of ALA, EPA-fed groups having the highest amount of EPA and DPA, which is another omega-3 precursor. And finally, the DHA-fed group had the highest amount of DHA. Again, in relation to the hepatic phospholipid fractions, the diets generally reflected what was in those fractions also. Again, with the ALA having the highest amount of ALA, the EPA-fed group having the highest amount of EPA and DPA, and finally, the DHA-fed group having the highest amount of DHA. But even though the DHA-fed group had the highest amount of DHA, you can also see here that the ALA-fed group had a higher amount of DHA than the EPA-fed group in the phospholipid fractions, which shows that the potential for the conversion is possible. Furthermore, you can also see that although ALA did have the highest amount of ALA found in the phospholipid fraction, if you look at the scale bars, the amount actually found is very minimal. In relation to the omega-6 to the omega-3 ratios, you can see that the DHA had the highest amount of omega-3s. But overall, in relation to the ratios among the omega-3 fatty acid fed groups, there was no significant difference. Again, you can see the DHA group had the highest amount of omega-3s in the phospholipid fraction also. But this was also similar to the ALA and the EPA fed groups. And again, you can see that the ratios of omega-6 to omega-3s did not differ amongst the groups. Finally, in relation to insulin sensitivity, you can see that there is no difference in fasting glucose among the FA-FA rats. And there was no difference in the AUC glucose, so the area under the curve, which was a measurement used to quantify the amount of glucose found during an oral glucose tolerance test. But in relation to insulin, you can see that the DHA group did exhibit lower amounts of fasting insulin. And this was similar to, oddly enough, the safflower LA control. And again, you can see that the EPA-fed group had the lowest amount of insulin in regards to the AUC insulin, so in relation to the amount of insulin during an oral glucose tolerance test, which again was similar to the LA control. So now to the end. In summary, we found that the DHA diet prevented the progression of hepatic steatosis as demonstrated by the similar total liver lipids in the DHA group to the baseline group. We found that the DHA-fed group had the highest amount of DHA in the phospholipid and the triglyceride fractions, highest total omega-3s in both the fractions, but overall, the omega-6 to omega-3 ratios did not differ amongst the omega-3 fatty acid-fed groups. We also found that rats fed the ALA diet had more hepatic DHA levels in the phospholipid fractions than the EPA-fed group. But the ALA diet did not improve hepatic steatosis parameters as similar to the DHA-fed group, which suggests that other mechanisms may be involved, and the fact that the conversion of ALA to DHA is not the primary reason for these improvements. Finally, we found that the DHA group had better insulin sensitivity compared to the other omega-3 fatty acid groups, which was oddly enough comparably similar to the linoleic acid control. So in conclusion, we found that dietary intervention with DHA was effective at reducing hepatic steatosis in FA-FA rats. And these positive outcomes were not obtainable in a high ALA-fed diet. Implications for human nutrition in the future include supplementation solely with DHA to decrease hepatic steatosis in patients. And this is something that further research, including human clinical trials, can be done. Furthermore, we also found that insulin sensitivity was also reduced in DHA supplementation. And as insulin sensitivity is closely related to hepatic steatosis, this can further amplify the effects of DHA in reducing and preventing hepatic steatosis. So now finally to my acknowledgements, I would like to thank my advisors, Dr. Carla Taylor and Dr. Peter Zaraka, the R.O. Burrow Laboratories at the St. Boniface Hospital for helping me with my animals, Dennis Labase at the U of M for his work with gas chromatography, my funding sources, so RD, the NSTRIC FAST program, and the University of Manitoba, my lab members, because you guys were great, super helpful, and my family and friends. Thank you so much.